Good morning, everyone. So first of all, I want to thank you for coming over this evening, and I'm happy that I'm surrounded by all these energetic, interested people, and also I'm a little bit intimidated, surrounded by all these gadgets, which I'm not really sure how it works. But nonetheless, I will stick with my subject, which is black holes today. And so I hope everyone has this flashcard with you, with the numbers.
Yes.
Okay. Because I have a number of questions during my talk, and it's not like I will grade them later and then made it back to you to humiliate you or anything like that. So I just want you to make your scientific guess if you don't really know the answers, and then we will figure out as we go together. So the main topic today is the physics of the black holes, and so I'm in the physics department as the other faculty members are. And but before we start, I just want to show you these people who are some of my collaborators. So this is not the single work that I've been doing on my own, and that also includes yes. So that includes some of the colleagues at NASA and JMU, and also the university in Maryland. And these two gentlemen, they're actually the JMU undergrad students who used to be working with me, and one of them is still working with me. So it's broad collaborations across the different populations, students and the scholars. Okay, so before I start anything, let me just switch back to this YouTube movie. And I'm not going to show you all the things, but maybe we can just watch for the first minute.
A robotic probe could transmit data back just before it goes over the edge. That edge of a black hole is called the event horizon. It's the edge of time and space, at least in the universe we know. We call the event horizon quite simply because it separates space into two regions. It's not a physical surface. You might not even notice it if you were falling through it. But ultimately, once you're inside, you're doomed. As you approach the event horizon, gravity gets stronger, and very strange things start to happen.
Okay, so I apologize for the audio. Since it's playing out of my laptop, I can't really tune up the volume. So the point of that movie is that now you have at least some graphical, artist concepts idea of what the black hole is. And you may have seen that already somewhere in science magazines or press release from NASA, or maybe in your astronomy class you have taken one before. So that's the primary place where my interest goes to. And before we go to specific subject, so here's my outline. So first I will talk about the general idea or general property of the black holes, and then for those who are still wondering about the existence of black holes or the physical relevance of the black holes, I will show you some evidence, observational evidences that the black holes do exist in astrophysical systems. And in the end, I'm going to take you into a little bit more details about the so-called physics of accretion disk, and you will know what the accretion disk is if you don't know at this point. Okay, so if you have this flashcard with you, you can just fold it, and you see 1, 2, 3, 4, and my first question here is about the nearest star to us, which is, of course, the sun. Because before we understand black holes, we want to understand the typical star, which is our sun. And so I have 5 choices, and if you choose 5, then you can just show me the back page of that flashcard. Okay, so so let's do this real quick. So in 6 gigayears or so gigayears, it's 6 billion years. So it's 9 zeros. Our sun will eventually become a giant molecular cloud, a giant planet, a black hole, a white dwarf. We don't know yet. Okay, show me your guess. Okay. Okay, is everyone making up your mind? Still thinking? It's okay to get it wrong. There's no right or wrong. Okay. Let's see. What does blue?
C.
That's C. Thank you. Or A, B, C. That's 3. Okay. All right. Thank you. So. So the right answer is a white dwarf, number 4, or D. And so it turns out that our sun is not going to turn into a black hole for very well-known reasons. So we will come back for that. Okay, so more details about our sun, and I don't want to spend too much time on this side, so let's just focus on some numbers in red. This is the schematic picture of the sun showing the photosphere, and so this is a visible horizon of the sun. And inside, of course, we cannot see, but there are means to probe the inner crust and also the properties of the gas in the core. Basically, the gravity is sustained by the heat. And that heat is coming from the thermonuclear reaction in the core by fusing hydrogen into helium. Okay, so the age is roughly 5 billion years old. So it's a kind of middle age, and 5 more gigayears to go before they turn into a white dwarf. The mass of the sun, in kilograms, it's just 10 to the 30 kilograms, and which I myself don't really have a clear idea of how big it is. But in the context of the Earth's mass, it's still big, 300,000 times the mass of the Earth. Now the size of the sun, that's 700,000 kilometers. Again, that's 100 times bigger than the size of the Earth. And the temperature, you may know, this is the temperature that we kind of measure from the optical emission coming from the photosphere of the sun, and that's about 6,000 degrees. So it's hot. Like I said, it's shining by burning hydrogen into helium, and because the mass of the sun, compared to the astrophysical standard, it's not big at all. It's not huge. And for that reason, it's not going to become a black hole, and it will evolve into a white dwarf. So you may think, well, how many of you have heard about white dwarfs? Oh, okay, great. So most of them. In astronomy class, maybe science class, maybe some through your project. Okay, so the white dwarfs. So this is one destination for relatively, but not too massive stars. And so the point of this white dwarfs, the property of the white dwarfs, as star evolves, basically it will be compressed even farther in by gravity, and it burns more and more hydrogen inside of it. And then hydrogen is fused into helium. Now, what? The helium, the star needs to fuse helium into the next heavier elements. In this case, it's carbon. And you can iterate this process from lighter element to the heavier elements as long as your gravity is strong enough to continue to squeeze that star inward. Now in the case of the white dwarfs, or the sun, I should say the sun, the mass is not that big. So after the carbon fusion, after helium in the core was fused into the carbon, and this sun picks up additional gravity, the gravity is not good enough to fuse carbon into the next heavier elements. So basically, as soon as the sun produces carbon in the core, I'm not talking about the crust or shell, in the core. That's it. That's the end of the evolution, basically, for the sun. And that's exactly what the white dwarfs are. It's too light to maintain nuclear fusion any longer. And so the outer layer will eventually be ejected away. So basically, white dwarfs is sort of the leftover core of the finished stars. And if you think about that, so the core is made of carbon, possibly oxygen, but not like any heavier elements like iron or magnesium or nickel. And since this is just the leftover core of the entire star, the size of the white dwarfs is typically 1% of the sun. So now it's a really compact object. And this is why white dwarfs are one of the compact objects. It's a very small size. And in astrophysical context, we typically see these white dwarfs as binary systems, which is interesting, rather than just sitting by themselves. So for example, Sirius, this is a good example. So Sirius A, that's a companion star, the regular star, and Sirius B, can you find it in this picture? Yeah, this small dot. And so this star is almost taking over that brightness, but we can still see this even in the optical. This is the image by Hubble Space Telescope, and we can still see it. We can also see that in the different eyes, and by different eyes I mean in a different electromagnetic band. So instead of, besides optical, visual, if you go to a shorter wavelength and you take a picture of the system, if it's hot enough, the system will produce X-rays instead of optical lights. So in this particular system, you can actually see A and B. So A is most likely the companion, the regular star, and B is the white dwarf. And this is the cartoon version of it. Okay, so, there's actually a limit to how massive white dwarfs can be, and it's called the Chandrasekhar mass limit, and it's about 1.4 solar masses. And there is a really, really well-defined physics based on quantum mechanics and relativity to actually calculate this 1.4 magic number. I'm not going into these details here, but we can actually derive this magic number from the first principle, which is a part of the beauty of physics. Even though we cannot touch, we cannot do experiments, we can use our fundamental physics principles and then get some numbers out of it. Okay, so those are white dwarfs. And then let me go on to the main menu, so to speak, the black holes. Okay, so I want to introduce black holes from two perspectives. So one in the context of astrophysics, and as I briefly mentioned earlier, the black holes are the ultimate final destination of massive stars, typically weighing more than 30 times solar mass. So of course, the sun does not belong in this category. Believe it or not, the black holes turned out to be, well, we never know for sure, but most likely, the most of the black holes out there in the universe are spinning, and even spinning at the maximum rate. And the third thing is that the black holes, if you think about the size of the black holes, they come in two flavors. One is a relatively small mass, which is what we call the stellar mass black holes. And we see them, we actually detect them, not directly, because by definition black holes are invisible. Black holes are black. So we cannot see them directly. But by other means, we are pretty sure that we are seeing the system that contains stellar mass black holes. And we see that in our galactic planes of our own Milky Way galaxy. Okay. So that's one flavor. And the other flavor, which is the other extreme, is a supermassive black holes. You may have heard that term somewhere. So it's a really, really massive, fat black holes. And we don't see them in our galactic planes. But it seems like every active galaxy, by active I mean the galaxy which emits a huge radiation from the center, from the nuclei, it seems like all the active galaxies have at least one supermassive black hole in it, at the center. And sometimes those active galaxies, they are called active galactic nuclei, AGN. So I may refer to AGN, but when I say AGN, that means active galactic nuclei, which hosts a supermassive black hole at the center. Okay? Okay, so those are kind of really, really brief summary of astrophysical aspect of the black holes. Now, we can also think about the mathematical aspect. And in fact, historically, black holes are first found as a mathematical solutions. If you know a little bit about the Einstein's theory of gravity, which is general theory of relativity, in 1915, it was Einstein who actually constructed the theory of gravitation, and under the name of the field equation or Einstein's equation, and basically that describes how to curve the space-time if you have a mass. So mass tells the space-time how to bend, and the space-time tells the mass how to move. And there's a feedback between the mass, any mass, you and me, or sun, or black hole, and the space-time curvature, which is invisible to us. It's a three-dimensional, actually four-dimensional space-time curvature. And so it was completely a mathematical construct at that point. And later on, three other people, they found different black hole solutions, and noticed that a year after the publication of the Einstein's general relativity, well, I'll show you in the next paper, someone already solved a solution in 1916. And however, the last major solution was actually found 1963, which is not completely, ancient history. it's still relatively new. So I think this really shows us, how rich this Einstein's theory of relativity is. So these are the main figures in those days. Of course, this is Einstein. And in 1916, I think this German physicist, mathematician Karl Schwarzschild, he actually solved the first exact solution using the Einstein's field equation, under some approximation and assumptions, of course. It's interesting that he did this in the battlefield, because this was in the middle of the World War I, and he was actually out there at the battlefield, and then maybe he was solving this equation while he was dodging the bullets. I don't know how that works. I couldn't do that, but he apparently did. And he sent his solution, not email, not internet, by snail mail. He mailed it, and then Einstein was very impressed. But historically, this is not really the first time when people start thinking about the black holes. Back in 18th century, like Mitchell and Laplace, they actually imagined, well, if there is any object whose gravity is so strong that even the light cannot escape against the gravity. So it was totally a thought experiment, and it was really classical thought experiment, but nonetheless, the 18th century physicists, they have already had this kind of idea back then. But now things are more mathematical and explicit. And then, as I said, in 1963, this New Zealand mathematician Roy Carr, he found the solution of the spinning black holes. And it turns out that this one, spinning black holes, seems like the most ubiquitous common black holes out there in the universe. Not on the equations, but in the actual universe. So these spinning black holes, they're called Carr black holes, named after him. Okay, so my question for you is, how small would you have to squeeze the Earth to turn it into a black hole? Less than 1 inch, 1 to 10 inch, 10 to 100 inches, or impossible? Okay, tell me what you think. Okay, so I think now I have a nice spread. Okay, D, I see D and A, B. Okay, A. Are you sure, Josiah? Okay, so it turns out less than an inch. So it's actually less than 1 centimeter for the sun. For the Earth. For the sun, so that means, I don't know if that question makes sense or not. So that means if I want to turn the Earth into the black hole, I need to squeeze this Earth by some means. I need to squeeze it until to that small, less than an inch sphere. Okay. So I need some kind of really, really strong devices that allows me to do it. But this is thought experiment. In the case of the sun, does anybody know how small you have to squeeze the sun to make it into a black hole? So it's about 3 kilometers. Okay. So the radius of the sun right now is 700,000 kilometers. If I somehow squeeze the sun into a sphere of radius 3 kilometers, then the sun basically becomes a black hole because it becomes so dense. Okay. So unless you squeeze the object to that high density object, it will never be a black hole. And in terms of the physical properties, on the other hand, black holes are relatively simple stuff. And the reason is because when we talk about the Earth or the Sun, we have to worry about all kinds of complicated properties, like the magnetosphere, the atmosphere, and what is it? The liquid iron core inside of the Earth, and all kinds of details, complicated properties. When it comes to the black holes, all those variables, all those quantities, they come down to only 3 properties. And those are the mass and angular momentum, or angular momentum is a tendency to spin, rotate. So the spin rotation parameter, and the charge, electric charge Q. So only those 3 variables, 3 physical quantities. So this famous relativist, John Leader, he said the black hole has no hair because it's characterized only by 3 quantities. Okay, so far, any questions about anything? Any comments or unrelated questions? Okay. So here's my third question. I expect some of you have seen this movie already. So it's showing us some region, some system from until 2013, from what year was that? 1995. Okay, so where is this region? Our galaxy, Milky Way galaxy, or M31, which is our neighboring galaxy, Andromeda, or M81, or just simulations? Okay, what do you think? Okay. Okay, so I think the majority of you got this right. And some of you said it's M31 and M81 and no simulations. Okay, so that's our Milky Way. That's what's called dynamical center of our Milky Way. And these dots, they are, so this is the actual, it's a series of snapshots taken by this Keck telescope up in the Mauna Kea in Hawaii in infrared eyes, not the optical infrared eyes. So technically it's the micron wavelength. So it's not in our wavelength, but infrared, you can actually resolve these stars, which is doing some weird motion, as you can see. Like that slingshot. Let's watch that again. So we don't see anything there, but apparently that star, it turns around and the other one turns around too, around the same point in space where we don't see anything. People trying to figure out what's in it, what's special about the point. Maybe there's some dark mass, regular stars, but for some reason they don't shine. But if you think about the regular stars, for example, they will quickly collide with each other, and they cannot last for enough years. So obviously, this observation shows that there is some kind of source of the mass which is gravitating all these nearby stars. And so the only explanation for this is that there is a supermassive black holes right there at the dynamical center, at that's the position of the star. And it turns out that the mass of that supermassive black hole, it has to be roughly about 400 million more massive than the mass of the sun. So 400 million solar masses, supermassive black hole. Then you can explain this stellar orbits in this region. And it's amazing that this is 0.05 arc second. Put this in our scale. This is about 100 AU, and 1 AU is the distance between the Earth and the Sun. So by astronomical standard, it's not really a huge space. And so in this small region, all these stars, they're experiencing the gravitational field by the supermassive black hole at the center. So now, since we mentioned the Milky Way, that's the schematics of our galaxy. So here, this is where we believe the supermassive black hole is to be located, just like that observation suggests. And about 8 kiloparsecs away from the dynamical center, we are here. And do you remember that we have also binary black holes in our galactic plane, which has a smaller mass, which is about comparable to the mass of the sun, not the supermassive ones. So they are living in this plane here, somewhere in this galactic plane. And we know exactly where it is by observations, but I just don't remember where it is in this map. So somewhere there. 15 up to 20 binary systems, they are believed to host the stellar mass black hole as a binary systems. So they live here, and the supermassive ones, which weighs roughly 400 million solar masses black hole, solar masses, that lives right there. Okay, and you can imagine that the similar galaxy is everywhere in the universe. This is just our own Milky Way galaxy, and you can also imagine that every galaxy, as long as it's shining bright, they are believed to have more or less the similar supermassive black hole at the center. Okay, so our Milky Way galaxy, it's not. In a sense, it's unique because compared to the other supermassive black holes, it's very light. Even though it's 400 million solar massive black holes, the other galaxies, they tend to have billions or even 10 billions. So we don't know why our supermassive black hole is wimpy, very small, slim. But nonetheless, each galaxy has the big one. Okay, the fourth question is, astrophysicists are able to observe and study black holes because black holes radiate so we can visually see. NASA has sent a probe into them. Aliens have secretly told us. Falling hot gas radiates around black holes. Okay. Let's see that. Okay. This is some interesting. I like. Yeah. Okay. So more or less, D or 4, and I see A and yes, you guys. Aliens. Yes, I like that idea. I hope aliens have helped us to learn more about black holes, but in reality, it's 4. And this falling gas, it's called accretion disk. And the reason why it's called a disk, as I will show you in a moment, is because it basically, as they fall onto the black hole, they're not just randomly falling from all over the place because of this angular momentum property. They're going to be sort of sorted out in such a way that they will concentrate on the equatorial plane, and it forms like a pancake-like structure or the CD-like structure. Okay. So it's not really a solid disk. It's not a solid disk, but it appears to be a disk-like structure. It's not a chaotic random structure. Okay. So we'll see that in a moment. So in astrophysical context, this is a stellar mass black hole, and of course this is an animation. It makes so this black hole makes a binary system with that companion star, and of course we don't see anything from the black hole. But the thing is, if it's a binary system, the donor star or the companion star, they have gas, right? They have material. So due to the gravity, the outer material of the companion star, they will be pulled in by the gravity of this black hole. And the gas, like I said, they just can't randomly fall in because of the angular momentum. And so they're going to form this nice and smooth pancake-like structure, and this is what we refer to as the accretion disk. Okay. And so one example, we know this is a well-studied binary system, black hole binary system, GRO 1655. We believe that this black hole has about 7 times the solar mass. So it's not a supermassive black hole, it's a stellar mass black hole in the binary system. And like I said, we have 15, 20 of them in our galactic planes. And I'm sure if we travel to the other galaxy, let's say M31 or 81, they may probably have number of the black hole binary system, just like ours. But we cannot travel there, so we just stick with our backyard. And this requires a little math, but I'm sure you can handle. So radius of the event horizon of that binary black hole is approximately 1,000 miles, 100 miles, 10 miles, 1 mile. So this is the so-called the radius of the event horizon. And I haven't really talked about the event horizon, but who has heard about the event horizon? Okay, not so many. Not so many. Okay. There's actually a Hollywood movie called The Event Horizon, and which has nothing to do with the black hole. It turns out to be the horror movie. So the horizon, event horizon, it's the radius, but it's basically the point of no return. So once you cross that line, the gravity is so huge that you can't get out. You're going to have to stay there, and bad things will happen. And that radius, it's actually proportional to the mass of the black holes. Okay. So like I said earlier, if the sun becomes a black hole, so the mass of the black hole, if it's just one solar mass, then the size of the event horizon, so the radius of the event horizon, that would be 3 kilometers. Okay. And in miles, it's roughly 2 miles. Okay, so how about this binary system? Okay, what do you think? I see A, B, D, it's kind of scattered. Well, I'm giving you this hint there, and this binary black hole, give or take, it's 7 solar masses. So, does that mean you didn't all of them? Okay, that's an interesting answer. Okay, so, well, it's seven solar masses, right? So that's order of 10. Oh, I should have. Sorry, I changed that wording for this slide, but not the other one. So on the order of 10 miles, right? It's because it's 7 times 3. And does that make sense to everyone? Okay. So this is astrophysics, so we don't really care about if it's 7.2134 or 10.21. On the order of magnitude, that's 10 miles. So putting this in perspective with the circle of roughly 10 miles with the Harrisonburg at the center, that's the scale of the event horizon. So yeah, I don't know if your house is inside the horizon. I think mine is very inside the horizon. So I'm out. So it's really compact, small. And of course, the size of the event horizon is proportional to the mass. It gets bigger for supermassive black holes. Okay, so since I don't really have too much time, let's get up to speed. Okay, so this is supermassive black holes, and you are diving into the central nucleus region from the galaxy. And in the last minute, you seeing this accreting gas, and right there, so you're already inside the horizon. And all the gas, they are sucked into the black hole inside the horizon. So I did not mention this particular name, Sagittarius star. That's the name of our supermassive black holes at the dynamical center, which has 400 million solar masses. And we have a number of more active galaxies. The most famous galaxy is this MCZ6. It's also well studied, supermassive black holes. Oh, and sorry. So the typical mass can be million, it can be billion, or even bigger. Okay, so question 6, which one of the following is a likely fact about Sagittarius star, which is a supermassive black hole in our Milky Way galaxy? The smallest black hole known to date, used by NASA for green energy. The brightest black hole known to date, a falling cloud was seen. Okay. Can you just guess? C. Looks like C and D, 4 and 3. It turns out our supermassive black hole is not the brightest, it's more of the dimmest black hole. But last year there was a falling cloud. It's called the G2 cloud. And the astrophysicists are all fired up and excited because if this gas falls into the black hole, crossing the event horizon, then we can actually study the space-time curvature, because this gas is crossing the event horizon where the gravity is so huge that the space-time curvature is really, really distorted. So we can actually learn some curvature by the supermassive black holes. But unfortunately, it didn't happen. So apparently this gas was actually made of a solid core in it. So initially they thought that it's a really tenuous, non-solid object, but it turns out it's solid enough to avoid any tidal disruption. So we didn't really see any flares or anything excited that we anticipated. So that was unfortunate, but nonetheless of science. Okay, so the last point of my talk is that we can study all this from the Earth in our view, in our eyes, optical or maybe infrared. These are on some of the pictures in optical and also radio band. But if you really want to study black holes, we need to zoom in. We need to go closer in, which is right here in the middle, right there in the middle. But the gas there, it's so hot, compressed and heated so much that it doesn't really produce optical radiation or infrared. It's more energetic lights, which is X-rays. So that's what I have been doing with my students at JMU. This is JMU Astronomy Clubhouse, department building. And as I showed you earlier, it's Peter and Doug. So Doug graduated, but Peter is still continuing to work with me. So they are working on this accreting gas physics. And just to show the highlights, one sort of signature of the presence of this accreting gas, because nobody really has taken the picture or tasted it or anything. This is all implication, but there is some observational signature that shows that the accreting gas is really there, just around the black holes. And one of them is called the ion emission line. So this is obviously the emission line, X-ray emission lines from ion atom. Not hydrogen, helium, carbon, it's iron. And so the idea is that this gas is orbiting around, circling around while it's falling. Right? It's not just a fall straight, it's spiraling in. So when it emits X-rays from the receding part of the disk, then the lights gets redshifted. It's a simple Doppler shift that you may have learned in high school science. And the lights coming from the approaching side of the accretion disk, it's blue shifted. Okay. So when you collect the lights from this system, you're going to see some peak in blue shifted part and the red shifted part. It's called the WP profile. And then I'm not going to the details about the